All right. Chapter 2 is smooth muscle. You guys ready?
Yep.
No, it's okay if you're not.
Yeah, I can be ready. I'll fix it
No,
later.
it's okay.
Oh, that was good. Oh, no. Yeah, I'm ready.
I'm making weird eye contact with the camera. There may be some funny faces. Okay, so chapter 2 is all about smooth muscle, which is kind of like a review from what we did in cardio phys last semester, but it's a little more difficult to understand. Okay?
Ain't nobody want to do cardiac.
Right.
That isn't sliding, is it?
It might have just a little. I think it's better now.
Okay.
I'll try and watch
put
it.
Something in front of
I mean, I got a water bottle.
Stay.
it.
Good dog. Okay.
All right, so there are 2 types of smooth muscle, and one of them is very common and one of them is very uncommon. Do you
Okay.
remember what those are? It has to do with their units.
Oh, is this
It's on the tip of your tongue.
I have no idea what you're
Okay, so there's single units.
Oh.
Gosh.
I was like, what? 2 times.
And there's a multi-unit. So what does that mean? Any ideas?
Yeah, so a single is kind of what it sounds like.
Probably. That sounds
So
like to me.
it is innervated by like tight junctions and stuff, right?
Mhm.
That's how it, because it
Mhm.
functions as a single unit.
So if we have lots of little smooth muscle cells here, they are all going to act like as one big cell. So there's going to be tight junctions, and there's going to be like other things connecting the cells, and if a innervation comes in and it activates and stuff is going through the gap junction saying to contract, they're all going to contract together. That's like
That
normal
is-
smooth muscle, like everywhere in your body is this kind of smooth muscle, so it's the most common. So multi-unit smooth muscle is a bunch of little smooth muscle cells, and they're all together, but they're each like separately innervated, and they don't have gap junctions. Oh, this should say gap junctions, not tight junctions. Sorry. And where is the only place that you find multi-unit smooth muscle? I think this would be a good exam question.
The intestine.
No. In your iris.
Oh,
So,
that's right. I remember that.
Yeah, if you remember, like your iris has those like constrictor smooth muscles, and since it's such a, like it needs such fine control to dilate just a little or a lot or just very, very minuscule amounts, it has to be just singly innervated, and it's smooth muscle because your brain doesn't want you thinking about, oh, what should I dilate my eyes right now or not? Because if you didn't dilate or you did and you weren't supposed to, like you would go blind. Because you would like, oh, I'm gonna look at the sun, and you wouldn't dilate you would dilate your eyes and you go blind.
I used to look at the sun and see if I could do it.
That's why you're colorblind, Cody. Come on.
Probably.
Okay.
That makes total sense.
Okay.
Now that I'm thinking about it.
And then so back to single unit, because this is the one that we kind of care about. What are the 2 types of single unit smooth muscle? Think of in your intestines, it's just kind of
Circular
going.
and longitudinal?
Not quite. So you have tonic and phasic.
Oh, that makes sense. Wow.
So what does phasic mean? Like in phases.
It contracts like in.
So it's gonna contract and relax and contract and relax, and it's just kind of gonna go at its own pace and not really follow any rules. And this is going to be most of your intestines. So it's called contract relax cycles. And what are some examples of phasic smooth muscle?
So it's gonna be in phases, so that would be like your small intestine.
Mm-hmm.
Ooh. Your stomach isn't phasic, is it?
Mm-hmm. Because
Yeah.
that distal stomach has like those phasic contractions. And then
So
there's
is it just the distal stomach?
yeah, I mean,
Okay, I just.
that's where the contractions normally happen.
Okay.
And
Oh,
then
and then your your rectus, rectum, rectal thing.
your sphincters or something else?
No, it's something else. The canal.
Just okay, I mean that's
Part of the intestines, I guess.
yeah,
That
but
makes
that's
sense.
fine.
Okay.
And then there's a couple other non-GI organs that are important phasic muscles. You don't have one of them.
Oh, yours.
There you go.
And then I was probably thinking like the bladder. like,
Yes.
yeah. That makes sense to me.
Okay, because normally your uterus and your bladder are relaxed, and then only at certain times do they actually contract, and the contractions are like in phase. Is that clear?
Mm-hmm.
Okay, so tonic smooth muscle. What does that mean?
Tonic means that it holds tone.
Mm-hmm. So it's always partially contracted. And what are some examples of tonic?
So
Smooth
those
muscle.
are going to be like veins.
Mm-hmm. Because you have to maintain blood pressure at all times.
Yeah. And then tonic is going to be your stomach, right?
No,
Like
because
the proximal.
oh yeah, maybe proximal stomach. I guess that would count. But just don't confuse that with
the distal.
the distal
okay, yeah.
stomach, because that's the more important
Okay.
of the stomach
Okay.
stuff.
Oh, so your sphincters.
Yes, perfect.
Yeah.
That's the big tonic one.
There's
Big,
7.
like big picture items for tonic smooth muscle are veins and sphincters, because they're always kind of contracted. And your veins like can change, but it would like you would die if your veins were like, oh, we're gonna contract and relax and contract all the way and then relax for a while, because your blood pressure would like go crazy and then you would die. So they always need to be somewhat contracted. And even if they relax, they're still contracted. And same with your sphincters for the most part. Okay,
I just poop everywhere.
please don't.
Incontinence.
Okay, I'm gonna erase this if this is
Yep.
good.
Yes, ma'am. I don't know why I can't understand it the first time around.
Because he doesn't explain it like this.
Okay. So then we're going to talk about receptors on smooth muscle cells that make them contract. So we also kind of talked about this in cardio phys, and it made marginally more sense to me then, but not a whole lot more. So I don't quite know where you guys will be with this, because it took me a lot of reading to like figure it out.
Okay.
So you have, if you remember from cardio phys, you have the L-type calcium channels. Do you remember where those are?
Those are long and they are on the cell membrane.
They are on the cell membrane. And what activates them? What opens the gate?
So it's calcium that does it.
So calcium is what's either coming in or out,
Uh-huh.
but what opens the channel itself?
See, I thought it was calcium induced.
There is a receptor like that, but that's not
Not this
L-type.
one,
Not
okay.
this one. So it's actually going to be voltage induced.
Mhm.
So pretend you have a nerve and it comes down and releases something that's going to change, like it releases an electrical potential. So your smooth muscle cell gets electrocuted, and that makes it go above a certain membrane threshold, which just happens to be like negative 40 millivolts.
Mhm.
And once this says, oh hey, it's really positive now, because it used to be like negative 80 millivolts, and now it's only negative 40, we're going to open the door. So the door is going to open, and then is calcium coming in or out?
So calcium is going to come in.
Yes. Okay. tell me how the L-type calcium channels work.
So L-type calcium channel, so it has an electric voltage, and so when the calcium comes in, it's making it positive inside relative to positive outside, and because of that, the ion will change the voltage, which will shut the door.
Which will open the door.
The calcium will?
So there's an electrical potential happening here, which opens the door, letting calcium come in. Because the door is naturally shut, but once your voltage is increasing, because it got hit with an electrical potential from your nerve, it allows calcium in.
Well, it's more negative outside than inside, right? Okay, I mean, it's more negative inside
than outside. Yeah.
So when calcium comes in, the way that that shuts though is because it made it positive on the inside and there's an ion gradient, right?
Yes.
Okay.
So just, you're thinking too far ahead.
Oh.
You're going too far ahead. So electrical potential comes down, that changes the potential inside the cell, opening the channel, and calcium's coming in.
Okay.
Is that clear? Okay. So what he calls the L-type calcium channel is VOCC, which stands for voltage operated calcium channel. Because it opens by a voltage change and it's letting calcium in. And that is really all you need to know about the VOCC channels at this time. Okay?
That it's voltage induced, and once the gate's open, calcium comes in.
Yes, if you have that and you know the different names for it, you're golden.
Alright.
Okay?
Is the camera still good?
Yes, it's still good. Alright, so the next one are what we learned last semester as GPCR channels. So that's going to be what he calls ROCC, which is receptor operated calcium channels. So what does that mean to you right now?
That it's like you have to have something come in and bind to the receptor, and then it opens the channel for calcium to go in.
You are really close. That was really good. So, we're going to still have our little neuron coming in and synapsing here. So we're going to call this here is going to be our binding site on the outside of the cell, and these three little circles are our G protein coupled, or are the G proteins.
Okay.
So this up here is the receptor. So your nerve is going to release acetylcholine, which is going to bind to this receptor and cause a conformational change, which will make your G protein phosphorylate some things, and then it's going to start a pathway because it's a GQ. We're going to talk about what that means too.
Okay, can you go back to that again? Alright, so the nerve releases the acetylcholine.
Yes.
Binds
To the receptor.
Okay, what happens after that?
Receptor changes conformational form, and it causes the alpha subunit to be phosphorylated, which makes it have an enzyme component on the beta and gamma subunits.
That's a lot.
Yeah.
Okay, so.
You don't have to know it in that much detail, but if it helps you understand what's going on. So why don't, okay, let me try that again. So acetylcholine binds to the receptor, causes the G proteins to make phospholipase C. How's that? Does that make more sense?
Yes.
Okay.
Got a stupid question wrong on the quiz.
Oh, I'm sorry.
Okay, I'm good.
Okay, so what phospholipase C is going to do is we have this other little protein hanging out that's called phosphatidylinositol, which is also like the abbreviation is PIP2. And it's going, PLC is going to cleave that into IP3 and DAG. And
What's
so
IP3 stand for?
it stands for inositol triphosphate.
Oh, I should have known
That was a question, I think.
that. Yeah, I missed that one too.
Is
Because,
it PIP2?
Mhm.
Like PIP, number
Mhm.
2? Okay.
It's inositol bisphosphate or inositol.
and what's the IP3?
IP3 is inositol triphosphate. Let me make sure that. I think that's what it is.
That's it.
Yeah, because he
That was
gave
what it
us
was.
the PIP2 name, and then
Mhm.
he asked what IP3 was, and I was like, I'm just gonna write the inositol because that's the only I word that makes sense to me.
Yes. And then DAG is diacylglycerol.
Okay.
Okay. So we've had acetylcholine come bind to our receptor and activate our G proteins, which made or activated PLC, which then is cleaving PIP2 into IP3 and DAG.
Okay.
So this is a receptor operated calcium channel. But
Okay.
you're like, wait, where's the calcium coming from? We don't have any calcium yet. So if you'll remember, every cell has an endoplasmic reticulum, and in muscle cells, it's called the sarcoplasmic reticulum.
Mhm.
So just remember this?
Mhm.
And it holds a lot of calcium.
Yeah.
Cool. Look at all that. So we're going to use these two things to get more calcium. So what you should know is that IP3 creates, or that's not a good word, it causes calcium to be released from the SR. So it comes down and it's going to bind to a receptor here and cause calcium to be released.
Okay.
And this, what's happening here is also a receptor operated calcium channel.
Okay.
But this is that calcium activated calcium channel you were talking about earlier.
Gotcha.
Okay? DAG is going to end up making something called protein kinase C that we will talk about in a little bit. Okay? Let me see what I'm missing. So do you understand the L-type or VOCC channels and the GPCR or ROC channels?
Yes, ma'am.
Okay. So this one is just an ion channel from voltage change. This one is a ligand binding, and that's causing a pathway that the end result is calcium release from the sarcoplasmic reticulum.
Got it.
Cool? All right. So the next two are not as important, and they're much easier to understand.
Woo!
Yay! So we have, in a couple of our classes, we've kind of touched on mechanosensory channels, which he calls SACC, which stands for stretch activated. And what that is say you have, you have all these smooth muscle cells, and they're all together, and they're gonna be our single unit, so they all act as one. And if something comes here and depolarizes on this cell, it's going to start contracting. And since it's connected to all these cells and connected to all these cells, it's going to be sending the same like depolarization through the gap junctions, but to increase the contraction and the speed of contraction, it's also activating channels in these cells that are stretch activated. So as this cell's contracting, it's pulling on these, and then they're pulling on these ones, and that's making more calcium come into the cell because they're being stretched. So it's like if you have, like your door is kind of like a rubber band, and you start pulling on the rubber band, and it creates space that the calcium can get through. Does that make sense?
Yep.
Okay.
So it stretches and everything has calcium going to it.
Yes, it just stretches and it opens like a ion channel that lets calcium in.
Okay.
Okay? That one's pretty, I think that one's pretty self-explanatory.
Yeah.
Okay,
Makes sense.
awesome.
Your diagrams and stuff help out a lot.
Okay, cool. The last one is not very well understood, so we don't have to know a whole lot about it, which is great. So it's going to be called store-operated calcium channel, which is SOCC. And what this is literally the only thing we know about it is that when your sarcoplasmic reticulum is getting low on calcium, it's going to send some sort of signal, we don't know what it is, up to the membrane that says let more calcium come in because we need more because our storage is low. And that's all you need to know about it.
Okay.
And those are your receptors, and if you can understand those, you're on your way.
Okay.
Okay?
Yep.
Is this all pretty good?
Oh yeah.
Okay.
Way better than it was.
Okay. So now before I go into the next part, I'm gonna just real quickly do a little aside that will help you understand the myosin light chain kinase and phosphatase regulation a lot better than if we just like go full bore right now.
Okay.
Okay? So we have these L-type calcium channels, and we have this GPCR that we just called a GQ. There's also GS and GI. Do you remember talking about those a little bit? We've been talking about them for a while, but no one ever really seems to explain like what they are, right? Okay. So in your cell, we're just going to call this another little GPCR, and it's going to have its same 3 little proteins, and we're going to say that it's a GS. So you're going to have some ligand coming in and binding to the receptor. It's going to cause things to happen in your G proteins, and since it's GS, what it has to do is it's going to activate adenylyl cyclase, which is an enzyme that makes CAMP. CAMP is cyclic adenosine monophosphate and is one of the most important like intracellular messengers. So CAMP does a ton of things, but the big picture item that you need to know is that it makes PKA, which is just protein kinase A. So we have protein kinase A, which comes from adenylyl cyclase and is from GS. S means synthesis of adenylyl cyclase or synthesis of CAMP. It just means synthesis. And then you'll remember from our GQ, we have protein kinase C. It's just like, we'll call this one A and this one can be C. Okay? You then have another one over here. We're going to call it GI. Again, a ligand will come in and bind to it. It's going to cause something to happen, but over here where we activated adenylyl cyclase, we are going to inhibit it. So if we inhibit adenylyl cyclase, we get no PKA. Okay? And it's not inhibit because it necessarily like turns off the cell, even though to an extent it kind of does. It's inhibit because it literally just inhibits adenylyl cyclase. So don't think of it as broad as it's inhibiting the cell, because it's not. It's inhibiting adenylyl cyclase.
Okay.
Just think of it as that specific.
Okay.
Okay? So there's a no PKA formed.
Okay.
Alrighty. Now the fun part.
This is stuff like we have to understand in order to be able to understand everything else.
Mm-hmm. Yeah, there's a lot here. Are you guys good with like how skeletal muscle, like the sarcomere and like actin binds to myosin, there's troponin and tropomyosin, and they have to move for ATP to, or calcium to bind the actin, and then that lets myosin bind to it?
Yeah.
At least kind of know what's going on there? Okay. Smooth muscle is different. So what you have is we're going to call this like a smooth muscle cell. And on the surface you have all these like circles, and they're literally called dense bodies.
Okay.
Okay? So from dense body to dense body, there's actin and myosin just kind of cross-linked, kind of randomly, but not. And what will happen is once actin and myosin start contracting, it's just going to pull the cell together until it's all contracted as much as it can.
Okay.
So in skeletal muscle, it's kind of contraction in 2D because all you need to do is like shorten the muscle. But smooth muscle is in a lot more of like circular organs, so you literally need to be able to contract in and around and up and down in all 3 dimensions. So that is why, or kind of why smooth muscle is different. So you have dense bodies that act into myosin bind to, and it just squeezes the cell. Does that make sense? Okay. Alright. So it's kind of arranged a little bit differently, but we're just going to say this is our actin, and this is going to be our myosin. And in skeletal muscle, there's a bunch of other proteins associated with the actin molecule that keep it from binding myosin. And in smooth muscle, you don't have any of that. It's literally just these 2 things. But there is a myosin ATPase area, so it's going to hydrolyze ATP and thus get energy. And it has to be phosphorylated for it to be able to bind actin and thus contract. So we had to find a way to add this phosphate group to myosin. Is that okay?
All this stuff's coming into,
Yes.
like I'm remembering.
Yes. We have to understand this to know how we get to here.
Yeah.
So this is our end goal, having this phosphate group. Yeah. And it's specifically at what is called MLC20, which is just a region on the myosin ATPase. So it's myosin light chain regulatory subunit or something like that is what MLC20 stands for, but it's just on the myosin ATPase. Okay, so how are we going to get myosin phosphorylated?
So this is where like the PKA and PKC come in.
It will. What is the enzyme that phosphorylates myosin?
So it's calcium.
You're getting there, you're getting close.
I think it's like a calcium.
You're very close.
It has MOK after it.
What's the MLCK?
Yeah, that's it. MLCK.
What is it?
Myosin light chain. No.
Yeah.
Kinase.
Okay, what's a kinase do?
It's enzymes.
A kinase always phosphorylates.
Phosphorylates. Okay.
Always. So we have hanging out in our cell, myosin light chain kinase.
Okay.
Great. But we can't just have, like, this can't just be going all the time. Because, like, if your smooth muscle is always contracted, that's a lot of energy to burn, and, like, that's bad news. You don't want it always contracted. So it's a very highly regulated. Very highly regulated. So you have this other enzyme called calmodulin, which is the one you were thinking of, that has to come in and work with myosin light chain kinase in order to turn it on. So it's going to be one of the things that activates myosin light chain kinase. And how do we activate calmodulin? Because it also has to be activated.
Calcium.
So calcium has to bind to calmodulin in order for it to activate myosin light chain kinase, which then activates myosin by phosphorylating the MLC20 region. Okay? And if you'll remember, where are the 2 places that calcium is coming from?
So calcium is coming from a VOC or a rock.
And the VOC is calcium coming in directly from, And then where is the rock getting calcium from?
Rock is getting calcium from my sarcoplasmic reticulum.
Perfect. Kayla, are you good with that?
Yes.
Okay.
Dude, this makes so much more sense.
If you're not, we'll
I
stop. Okay. So calmodulin is inactive until calcium comes and activates it. Then it goes and is able to activate myosin light chain kinase, which is going to come in, phosphorylate this group, and then ATP will be able to bind and be hydrolyzed and cause contraction. Alright, now we're going to add a little bit more complexity to this. So myosin light chain kinase can only be activated by calmodulin if it's in its dephosphorylated state. So it's only activated if it's in the D-phospho state. Okay?
Yep.
Okay. So that would lead us to believe that at some time we have MLCK and it's phosphorylated. And that is called the phospho state, and that's inactive. So how do we get it to be activated?
PK.
Which one?
This is a good one. I'm gonna say PKA.
Why?
Why would I
Why?
say that? Just because, it's a
It's gonna
stimulatory.
be
I don't remember.
PKC.
It is PKC.
Dang it.
So, along with not thinking of the GI as inhibiting the cell, don't think of GS as stimulating the cell to contract.
She's stimulating.
That's
the
trapped.
cyclase.
It's only stimulating adenylyl cyclase.
Okay.
So, to make this easier for you, this GQ-GPCR is already making calcium. So it makes sense that the other arm of that GPCR is making the thing that's activating MLCK.
Okay.
So this is like multitasking. They're like, we're one, gonna make calcium, exactly, and then they're two, we're gonna go turn on MLCK. So there's no reason to have one if you don't have the other. So it's going to come over, and there's more steps involved, but this is the only time a kinase is going to dephosphorylate something. It's really not dephosphorylating something, but I don't want to confuse you with what's happening because I don't think it's that important.
Okay.
Okay? But PKC is coming over and removing the phosphate group, thus activating MLCK.
Okay.
Okay? So this is how so the calcium calmodulin and PKC making it into the dephospho form are the two things required for MLCK to be activated and thus phosphorylate myosin. So that is what causes contraction. Is that clear?
Yes.
Okay. The next step is, so what's like the sister to myosin light chain kinase?
Myosin light chain phosphatase.
Perfect. What's a phosphatase always do?
Phosphorylate something.
Yes. And wait, a phosphatase does what?
Dephosphorylates. something.
Dephosphorylates. Took me a minute. Okay.
I was wondering if that was right. And you said yeah, and I was like, oh. Huh. Makes sense the other way.
Okay. Phosphatase always dephosphorylates.
Dephosphorylate kinase phosphorylates.
Phosphorylates.
Okay, got it.
Yes. Okay. So it's dephosphorylating is that active phosphate group on your MLC20 region of the myosin ATPase. Does that make sense?
Mm-hmm.
Okay. So it also stands to reason, because there's an active dephospho and inactive phospho myosin light chain kinase, that there's probably an active and inactive myosin light chain phosphatase.
Mhm.
Agreed? Because we have to have a high level of control. Okay. So just taking bets, is the myosin light chain phosphatase, is it active in the phosphorylated or dephosphorylated?
Dephosphorylated.
It's actually going to be activated when it is phosphorylated.
From myosin light chain.
Yes.
So okay, so it dephosphorylates, but it has a phos.
A phosphate group is just a switch. Phosphates just turn things on or off.
Okay.
So this little PI on MLCP is just turning it on.
Okay.
When it's on myosin light chain kinase, it just turns it off.
Gotcha.
Okay? When we go over here to the MLC20, it's just removing the phosphate group on an MLC20 and turning it off.
Okay, so P with P is good.
Yeah.
It's on.
Yes.
Got it.
So that's going to be active. And then its dephospho is inactive. So back to our multitasking, I think, yeah. If calcium released from IP3 and PKC from DAG are both causing contraction, they're also going to be inhibiting what's causing relaxation because they want to be in charge.
Okay.
So what PKC is going to do is it's going, again, it's kind of, I could explain it, but it might just confuse you on what's actually happening, but it's causing this dephosphorylation of myosin light chain phosphatase to occur.
Okay.
Do you want me to tell you how that works?
Nope.
Or okay.
Unless Kale wants it.
Do you want it, Kale?
So PKC
Is dephosphorylating myosin light chain phosphatase.
so it acts on the phosphorylated form to dephosphorylate it?
Yes.
Okay.
And I can tell you how that works,
No, that's okay.
but
I'll need to know all that.
okay.
Unless I need to know it for the test.
It might be a question,
Yeah, then no.
but I think
I'll guess.
I think understanding this is more important than getting that one little detail and confusing the rest,
Yeah.
in my opinion.
Agreed.
Okay. Okay. All right. What have we not talked about yet? Oh, one thing we haven't talked about. So now that we're kind of in the relaxation phase, which we have our active myosin light chain phosphatase, which is removing the phosphate group from myosin light chain 20, it also stands to reason that we're going to need to deactivate myosin light chain kinase because we don't want it turned on because we're trying to relax. We have all this stuff going, right? Okay. So based on the protein kinases that we have left, who do you think's doing that?
PK.
Good job.
Woo, got one right finally.
So it's going to come over and cause myosin light chain kinase in its active form to be phosphorylated into deactive myosin light chain kinase. And as you can see, GS stimulates, but it's inhibiting contraction. So that's why I say just think of stimulates as stimulating adenylyl cyclase. Okay? Okay.
So PKA
Mm-hmm.
phosphorylates MLCK to
Mhm.
the inactive form. Okay.
Yes.
And PKC dephosphorylates
Yes.
to the active form. And it's just opposite.
PKC phosphorylates to the inactive form.
There you
Not
go.
MLCK.
On which one?
MLCK
It's doing what?
dephosphorylates to the active form.
Yes. What does it do to MLCP?
It phosphorylates to the inactive form.
Perfect.
You're fine. I didn't say which one I was talking about the second time.
Okay. I'm trying to think of some questions we could ask from here.
PKA does not affect the phosphatase. MLCP does it.
No,
Okay.
there's I'm getting ready to add in another protein kinase.
Okay, that's fine. I was
Okay.
just making sure that.
Yes, you are correct.
Okay.
So we know how to turn on MLCK. We know how to turn off MLCK. We know how to turn off MLCP, but we don't know how to turn it on.
Mhm.
So what that's going to be is this takes a little stretch. So this is also going to be membrane because I ran out of room here with the membrane. Okay. And you're going to have another GS channel. And there's going to be 3G proteins just like normal. But it's going to be coupled to a different enzyme. It's going to be coupled to what's called guanylyl cyclase.
Mm-hmm.
Remember that?
Yeah.
Which is going to make CGMP, which is cyclic guanosine monophosphate,
Yep.
which is going to turn on some enzyme that I don't remember the name of, and it's going to make PKG. And what you should know about this pathway is the ligand that's coming in here and activating is nitric oxide, our good old friend.
Okay.
Okay? So where is nitric oxide coming from? Just a refresher.
Other cells beside it?
Mm-hmm. So it's important in the blood vessels. So in blood vessels, nitric oxide is synthesized by the endothelial cells, and then since it's a gas, it just like diffuses into the smooth muscle cells where it's binding to this GS receptor and making PKG. So if you remember, nitric oxide's big thing is that it relaxes smooth muscle. So it is going to be what comes over here and is activating myosin light chain phosphatase.
Okay.
Okay?
Yes, because when MLCP is activated, it is relaxing the smooth muscle.
Mm-hmm. Mm-hmm.
Okay.
Okay? So there's a whole lot here. And what you're best to do is go write it out, list it, draw it a million times until you can say what every single protein kinase or myosin light chain kinase is doing.
Okay.
Or re-listen to this a million times, or because there's a lot here to try and pick up on one time through it.
Yeah.
And I'm sorry about the arrows. I have a more neatly drawn one that I can send you guys.
That's up to you.
Yeah.
I would love it if that's what you want to do.
Here.
Oh, wow. That's neat.
Have you seen that thing?
Absolutely.
Did you take
One
like
of
10
them?
pictures?
Yes.
I
I
don't
did.
necessarily need like all 5.
You never know, okay?
Okay.
They're all actually good pictures. I'm not good at pictures.
And then the last thing we should talk about with protein kinase G is an important part of relaxation is getting calcium out of the cell, because if there's calcium still in the cell, it's over there trying to activate calmodulin and myosin light chain kinase, and we want that to not happen. So what PKG is going to do is, here I'm drawing more membranes. So pretend this is another membrane and this is inside and this is outside. And you have a channel here, it's called NCX, and that's going to be sodium calcium exchanger. So it's pumping calcium out and it's pumping sodium in. Because if you remember, sodium's really high outside the cell and it wants to come in, so we can let sodium in and use that energy to pump calciums out. So it would be like a secondary active antiport. Okay?
Antiport because it's going different directions.
Yes.
Kel told me that.
And PKG is going up and like helping this happen. That's not P or K. It's going up and allowing this to happen, like turning on the channel, making it more active. And then the other thing that PKG is doing is you have these circa channels in your sarcoplasmic reticulum, and it's going to go turn that on so that it can actively pump more calcium into the sarcoplasmic reticulum.
Okay.
Okay? And that's, I know that's a lot, but if you get this, you'll get everything else so much better.
So PKG turns on circa to put calcium back in sarcoplasmic.
Yes, yes. And circa is like a,
Which is the total opposite of what IP3 is doing.
yes, exactly.
Okay.
Does that help?
Yes.
Yes.
Okay.
So the circa means sarcoplasmic reticulum calcium.
I don't remember what it means.
Okay.
I'm sorry.
Oh, nope, that's fine.
Something like that.
I don't need to know. It's fine.
Okay.
Yeah.
And like, there's a few other like little things, like we skipped kind of how PKC is working, and there's some other stuff inside the sarcoplasmic reticulum. I don't find it that, it's just kind of nitpicky. Like, he could certainly ask it, but like I don't even know it necessarily well enough
Yeah.
to teach it.
Good.
So
And that's like we can, if as long as like this is the base knowledge, we can go back and figure out
If
what
you-
we can add.
if you get this, you will be like golden
Okay.
for this section. And I think there will be a lot of questions from this because it's really important.
Yeah.
And then, sorry, but on that picture that he took, there's like a green side and there's a red side. And for the most part, the green is everything stimulating contraction and the red is everything inhibiting. Because I use colors
Yeah.
like
No, you're
That's
good.
to code what things are for. And then the blue is just the, like what actin and myosin is doing.
Okay.
Okay. That's how smooth muscle cells contract and relax in a nutshell.
Fantastic.
Fantastic.
I hope
Yeah.
that helps you guys.
It does.
Okay.
Well, thank you.
What do we have tomorrow? Tomorrow's Wednesday.
Yeah.
So I'll probably like eat lunch and then go to anatomy to review for a while, and then if you guys want to like do this directly after that, that'd be fine with me.
Okay.
Is that okay?
I'm sorry.
Are you okay?
Yeah.
He was not listening.
Okay.
Yeah.
So we have class until 11 or until 12 tomorrow. Then
Mhm.
we have like a lunch, and I'll probably eat lunch and then go directly to anatomy and review for a little bit. And then if you want to do this like right after reviewing, would that be okay?
Yes.
Okay.
That would be perfect.
Oh, I'm gonna stop this.
Okay.